Good evening, ladies and gentlemen. Great to see such a wonderful audience here tonight. I'm Mike Brooks. I'm the Deputy Vice-Chancellor for Research here at the University of Adelaide, and it's my great pleasure to welcome you to the final Research Tuesday for the year, and that is Kaleidoscope. Can I first acknowledge the Kaurna people, the original custodians of the Adelaide Plains and the land upon which the University of Adelaide's 4 campuses are built. It's been a big year for Research Tuesdays, and as always, we've had a variety of fascinating topics. We've touched on stem cell therapies, managing earthquake risk, the latest in light technologies, and a commemoration of World War I. So it's been a really varied year. Tonight we turn our attention to particle physics and the Large Hadron Collider. Our speaker, Dr. Paul Jackson, is an ARC, an Australian Research Council Future Fellow, and an academic and a researcher within the Australian Research Council's Centre of Excellence for Particle Physics at the Terascale. Paul is currently part of the ATLAS experiment at CERN, where he works with the Large Hadron Collider, and I must say I was privileged to visit the Large Hadron Collider and the ATLAS experiment just over a year ago, and for me it was as good as opening your Christmas presents when you're a 5-year-old. It was fantastic. So Paul spent 3.5 years prior to taking up his position at the university working at the LHC, the Large Hadron Collider, and tonight he's going to give us an idea of how the LHC works, what it's being used for, and to talk about the Higgs boson. So please welcome Dr. Associate Professor Paul Jackson.
It's my distinct pleasure to be here to talk to you tonight, the last of the Research Tuesdays of the year, with the title Kaleidoscope. So what does this mean? As a high-energy particle physicist, I've spent most of my career looking into elementary particles and how they interact at the fundamental level. And I've done this for the most part with particle accelerators and particle colliders, such as the Large Hadron Collider that you'll see on your left here. But I've more recently been interested not just in the small scales that the Large Hadron Collider can probe, but also the larger scales that we see in the universe, and how these two are intimately connected and related, and how we can bring these together in the studies that we do in the laboratory. So tonight I'm going to give you a 21st century view of what we see as the understanding of nature, and give you some idea of what the fundamental questions in the physical sciences are today. So those questions can be written down in this way. They're essentially very human questions. They're things that we've been thinking about for many generations. What is everything made of? What holds it all together? And why is that the case? What are the laws that govern these things? Okay, so these are really kind of fundamental questions of anyone who's sat over a cup of tea or just sat outside and looked into the sky and thought about these things for a while. And this takes us towards the frontier of energy and size. And so in order to do this, we need a piece of experimental equipment. So we'll start off with a Hello Kitty microscope here. And we're going to try and probe down to a smaller scale by looking with this piece of equipment that we have. And what we found over the course of the last century or so is as we probe down in smaller scales, we can go deep into the atom and see that there's a nucleus there. Inside these nuclei, they're made of protons and neutrons, which themselves are composed of quarks, which, as we can see at the moment, are the fundamental particles of nature along with the electron. But there's a question mark here. There could be something else for us to see. And essentially, in order to see these things, I've put up one of the few equations that I'll show in this evening's talk. For light, an equation of energy times wavelength is equal to the speed of light. So the speed of light is a constant in nature. This represents an issue for us to be able to get to smaller scales. Because if we want to reduce this wavelength, this distance, to a smaller scale, and we have a constant speed of light, we need to up the energy to be able to probe these small distances. So even just quite a simple equation sort of tells us a lot of the important things that are going on in high-energy particle physics. And so this gives us a bit of a survey of what we've done using this probing to smaller scales with higher energies over the course of 50 years or so. And it's essentially a snapshot of all of the discoveries that have been made in high-energy particle physics across a wide variety of experiments that we've used. And what I'll talk about today is an experiment called the ATLAS experiment that Mike mentioned I'm a member of. And what we were able to do with this experiment is over the first 6 months to a year of operation at the LHC, because we had a higher energy, we could survey and probe all of these discoveries that have been made very quickly because we had access to all of the scales at which these different particles were manifested at. And this essentially leads us to an important point to make, that it's the experiments that lead us to an understanding of nature. We didn't just dig under the ground and find this Large Hadron Collider there. Man built this and put it there so that we could test nature. And we've done this through the last 30, 40 years or so with a wide variety of weird and wonderful experiments, from the Gargamel bubble chamber, which you can see now on show outside of CERN, to a set of kaleidoscopes, a set of collider detectors that have been used to probe different energies and scales. The UA1 and UA2 experiments at the superproton synchrotron at CERN, the L3 experiment, one of 4 collider experiments at the LEP ring, the Babar experiment at SLAC near Stanford University, where I used to work before starting working on the LHC, where we have 2 discovery experiments, the CMS experiment and ATLAS, that I work on, that I'll be focusing on talking about today. So it's really these experiments that have led us to this understanding of nature, and also a better knowledge of technology to be able to probe these smaller scales and bigger energies. And these experiments have led us to try and do really quite fantastical things, from the lower right image, which is showing very high energy cosmic rays impacting on our atmosphere and showering particles that we can measure, to interesting observations of the bullet cluster up in the sky, that we can see various gravitational effects that will lead us to interesting conclusions that we've drawn. Looking back in time with some satellites that we can send up to measure the cosmic microwave background radiation and look at structure formation in the universe. And in the video that you're probably enjoying to the upper right, where we accelerate protons around a large ring, and these protons are made of constituent particles, and we'll then bring these protons into collision inside these vast detectors that we build to be able to understand what happens when we rip them apart and see the fragments of these collisions that are made. And inside our detectors, we can create a set of particles. In this case, there's evidence of 2 muon tracks and 2 electrons. The muon tracks are the long things that are sticking out to the outer part, and the green blobs are 2 electrons. And this is one of the candidates in our data that we believe is evidence for the Higgs boson. So all of this work and instrumentation and studying different detectors has led us to quite an elegant picture of what the universe is made of. We call this the standard model of particle physics. And it has 2 rings of objects in this picture. The outer ring is all the matter that we see in the visible universe. This is separated into 2 parts. The quarks in the upper salmon or orangey color, depending on your eyes. And the 2 quarks that make up everything we know are the up and down quark. This makes up all of the protons and neutrons that manifest everything you've ever touched, everyone you've ever loved, everything you've ever seen is made of these things at their fundamental core. Surrounding these are electrons that go to make up all the atoms we know. And the electrons have some heavier cousins, the muon and the tau. And each of these charged leptons have a partnering neutrino that we heard a very nice talk about from Dr. Gary Hill in the Department of Physics on a Research Tuesday not too long ago. In the inner ring here are some bosons. They're the force-carrying particles of nature. So all this matter, whenever they interchange or exchange information, this is propagated by a boson. So the photon, carrying of light, we know as the propagator of the electromagnetic force. The gluon here is the glue that holds these quarks together inside the hadrons that they manifest. And the W and Z, or Z boson, depending on your flavor, are the 2 bosons that propagate the weak interactions, so responsible, for instance, for nuclear reactions. And underpinning all of this is a mysterious object called the Higgs boson that interacts with all of these particles, and at the fundamental level, it tells them what mass they need to have. So, with recourse to mathematics, we can take all of these particles, and through many years of study, we can write down an equation that governs the interactions of these matter particles through the exchange of forces. This is what the equation looks like. It's the equation that governs the interaction of all of these particles that we know of in the universe. Since it can fit on this nice coffee mug, I think it's fair to say that it's pretty simple in an equation. It's quite elegant, at least it looks quite pretty, whether you understand the mathematics or not. And it's also symmetric, but key to an experimentalist like myself is I can talk to my far more advanced mathematically particle theorist colleagues, and they can take this equation and they can predictively tell me what will happen if I perform a certain type of experiment, if I do something in my experiment, such as if I collide protons together at a certain energy, they can predict what should happen at that energy. And then I can go away and do this with my experiment and test that prediction. And that's really the interplay between experiment and theory that we're doing in particle physics. But how is it that a collider can tell us about particles? I think intuitively, you probably all have a sense of this. You've seen this equation from Einstein, who's going to crop up a few times in this talk, E equals mc squared. We already saw that c, the speed of light, is a constant. So what this equation is telling us is that you can trade the energy of motion here, put into two protons that are whipping around a ring, and when they're collided together, this can be manifested as mass energy of two heavier particles that we can produce, trading energy of motion for mass of something we can produce. In this case, showing a pair of the heaviest quarks that we've ever seen in nature, the top quark. So this is where we do a lot of this work. This is the outline of the Large Hadron Collider at CERN. It comprises two beams of counter-rotating protons just outside Geneva, Switzerland. It's 100 meters underground, so it's not a big red line ruining this nice landscape. And this 100 meters underground is then a place where we recreate the conditions a billionth of a second after the Big Bang. It's 27 kilometers in circumference. And to give you an idea of what that means, there's an outline of the runway of Geneva Airport to put some sort of scale to this. And when we bring these protons around the ring and into collision, we need to see what happens when we collide them, so we have our kaleidoscopes, our detectors. And the two multi-purpose detectors at the Large Hadron Collider are the CMS experiment and the ATLAS experiment here, which I work on. So to bring this a little closer to home, I appreciate probably not everyone has been to Geneva, Switzerland. This is what it would look like if we were to transport this magically to Adelaide and have some access to a Large Hadron Collider of our own here in our own backyard. And we'd have competing experiments up in Prospect and down near Unley, presumably where some of you live. So I'd just like to take a momentary break here. I'm going to throw up a couple of these throughout the talk. This is really, if you haven't been listening for the first 10 minutes, a one-line summary of what I've been talking about. Or if you'd like to share some of your thoughts on Twitter with hashtags and all these other things, this is my Twitter handle. High-energy particle colliders produce the smallest building blocks of nature. In summary, that's really what we've been talking about over the first 10 minutes or so. So I'll give you a chance to take a picture of that if someone wants to. And so when we've produced these highest energy particles, when we've produced them, we need something to be able to detect them, and that's what our ATLAS experiment does. This is a picture during the construction of ATLAS back in around 2005, and we can see here a gentleman stood at the bottom to again give an idea of scale. If you're looking directly into the screen, which hopefully at least some of you are, then right down in the center here is where the beam pipe will be going once the detector is completed construction. And so this is probably about 10 years ago this picture was taken. So this is the collaboration that we put together to be able to construct such an enormous piece of equipment. The Large Hadron Collider and the experiments that benefit from it need a lot of people working all over the world. Here's Australia at the top of the world. And as Mike mentioned, we are part of an Australia Research Council Centre of Excellence for Particle Physics. And so this allows researchers here at the University of Adelaide to collaborate and work with our friends and colleagues in Melbourne and Sydney and work on this big experiment over here in Europe. And also collaborate with people from 38 countries all over the world to be able to construct this massive detector and then operate it and ultimately bear the fruits of what comes out of this experiment. So this is what it looks like, and this is what we see when we collide beams together inside this large experiment. It's essentially a very, very big, complicated camera. Okay? It's 44 meters in length and 24 meters in height. And we also mentioned that this was 100 meters underground to be able to shield it from any background cosmic rays. So it's a very vast undertaking of engineering, even just to get this thing down into position. And we're trying to measure things at incredibly good precision. But our big camera is made of stuff. There's things like a pixel detector, a liquid argon electromagnetic calorimeter, and a muon detector. So what are all these things doing? Okay, so they're put together to serve different purposes, essentially to resolve different aspects of the photo that we want to take with these collisions. And again, here's some people generously giving us a size of scale here. So when we've got a little closer to completion of this detector, we can see a lot more complexity of the hand-soldered electronics that are required to go into building this. And we can see we're taking snapshots of proton-proton collisions, but essentially we're doing this, and we need to do it very quickly and in 3 dimensions. So we're getting 400 million proton-proton collisions a second. The protons travel around the 27 kilometers of the LHC ring 11,000 times a second. They're moving at the speed of light. So we're taking an awful lot of data, and we need to be able to process this very quickly. And we have these different pieces of the detector. So if you imagine cutting it down the middle and taking a slice, like a piece of cake or a slice of pizza, and looking at the different bits that manifest the detector, it looks something like this. And this might look complicated, but it can be broken into 3 different parts. So this white dot at the bottom of the screen here, this is essentially where the beams would be colliding in the center of the experiment. We've taken a slice of it. And the first things that the remnants of these proton-proton collisions will see is a tracking chamber. So a tracking chamber is immersed in a solenoidal magnetic field so that we can bend positively and negatively charged particles in different directions to measure their charge. The amount by which they bend allows us to measure their momentum, and we can track them through the silicon microelectronics of this 80 million channel detector to be able to measure the position of every charged particle we produce. Outside of this, we have some calorimeters. So calor might give you a hint about heat. This is essentially a big thermometer. It's measuring the heat or energy that's being deposited by showers of particles that are passing into our equipment. And these can come in 2 different forms. Electromagnetic calorimetry, which measures electrons and photons, things that interact electromagnetically. And then hadron calorimetry. So from the Large Hadron Collider accelerating protons, you've probably already surmised that protons are hadrons, and there are various other types of hadrons that we can measure. And we want to contain all of their energy inside this calorimeter so we can see how much energy there was here. We have these muons that will pass all the way out of our detector and be measured in the outermost reaches of the ATLAS experiment. And then one very important part of the puzzle here are neutrinos, or things that we don't measure. These can be neutral objects that will pass out of our detector, and we can only really infer their presence by measuring everything else that we see in an event, knowing that it should add up and balance because of energy and momentum conservation. And that if we see there's an imbalance, we can infer that something has been missing inside a particular collision that we measured. And so these neutral objects like neutrinos or other things will be quite important for a bit of discussion I'll have later on. So to dissect an image quickly from the camera, it looks something like this. If we again take a sliced view, this is a picture that we took with collision data a few years ago. And so we can see there are charged particle tracks in the middle of the detector. There's a muon candidate that's passing to the outer reaches. And there are jets or showers of particles being measured in these calorimeters. And if you took this image on the left and you were to slice your calorimeter and flatten it out, almost like a rug if you just rolled it out and made it flat, you could see an image like this, where these 2 different chunks of energy would be manifested at 2 different parts of your detector. So this is just giving different views to be able to see what it is we're measuring. And when it comes to measuring, we also want to measure not just position, momentum, and energy and charge. We want to measure the mass of things. Now, when it comes to measuring masses of things that we know, we might take some piece of equipment that we have and take a known mass that we have and try and calibrate that bit of equipment based on knowing a particular mass of an object before we go and convince ourselves that the sugar or the rice or whatever else it is that we want to measure on this scale is going to give us an accurate reflection of the mass of that object. So this is exactly the same thing that we do in these high-energy collisions. We have, as a survey across the mass of two objects here, the mass of two oppositely charged muons, we can see a distribution that has some bumps in it. And these bumps are essentially akin to our calibration objects that we can use to be able to measure how well our detector is being able to respond and give us a measurement of mass. Essentially, these are things that were discovered way back when in this earlier slide that I showed, and so we know their masses very, very well, and we can use this to understand the performance of our detector and experiments and then move from there. And particularly the Z boson here, which is one of the heaviest bosons that we've measured until recently, is quite an important thing to probe. But then predicting and measuring things in this standard model is something that I talked about with our equation on the coffee mug. And this is crucial for what we do at these high-energy collisions. So the precision measurements of these standard model particles are very important. This is a very big and complicated picture. It doesn't need to be. On the y-axis here, this is the number of times something happened. We're comparing these blobs of gray that you might be able to see on these plots to the data that we collect, which is essentially saying we're measuring what we predicted, what our theory says we should see, with what the data says we did see. So we take data and compare this with our prediction. And we can see for the blue data at a lower energy of 7 tera-electron volts, and the orange data at a higher energy, we have very good agreement with these predictions for various different standard model processes. So this is crucial to demonstrate the accuracy of the experiment. We're able to measure something from the very well understood theory that we know should be there, but also it's crucial to demonstrate this precision such that if we ever wanted to claim discovery of something outside of this standard model picture, we've already convinced people that we can measure things that they know are there from previous experiments that have been done. So, my next tweetable, which gives me a great chance to get some water as well, is particle detectors at CERN record and dissect the results of high-energy collisions. Okay. So, once we've recorded and dissected these results, we need to then start doing something quite vast with them. And this is what we do, what we did in what we're now referring to as Run 1 of the Large Hadron Collider. So this lasted from 2010 until late 2012. And the point of this was to probe at these higher energies than we'd done before, and really to try and understand nature at these higher energies. And the key observable from the highlights of the LHC Run 1 was that of the Higgs boson. Now, the Higgs boson is, like all of the other bosons, a propagator of a field, in a sense. And the Higgs field can be thought of as something that permeates all of space. Indeed, it would look something like this. It would be a grid that would permeate all of space, and it would interact with particles that pass through it all the way through space. So if we had a massless particle, for instance, where the Higgs field and exchange with the Higgs boson would not happen, that massless particle would just pass right through the field without being impacted. Whereas if we have a massive particle, like this example here, the Higgs field will be exchanging Higgs bosons with this particle to tell it at the fundamental level what its mass should be. It's essentially akin to an electric field, if you want to think of it this way. A neutral particle would pass through this without being deviated, whereas particles that carry charge are deviated by this electric field in some fundamental way that tells them they have a certain amount of charge. Essentially, that's what the Higgs field via exchange of Higgs bosons is telling us. So this is quite a busy slide, but I'm going to walk you through a couple of these things that meant the manifestation of the discovery of this particle. If we just focus on this picture in the upper left-hand side, we have some data points, which are the dots here. And there's a smoothly falling distribution that has a bump in the middle of it. And this bump disagrees with what you would expect to see if there were only background particles. And in order to reconcile this with what we see in the data, we have to fit some small bump here at around 125 in these units. And this is in a decay going to two photons. If we were to look in a similar type of decay, where we would have 4 leptons, like 4 electrons, 4 muons, or 2 electrons and 2 muons. So these are the charged leptons of the standard model. These data points, again, agree quite nicely with this background, the red blob, all except at one point, where we have this blue spike. And the data point here really requires there to be something more than just what is shown by that red distribution. There has to be an additional piece in nature here to be able to allow our data to be well explained. And here's a picture or an example of one of these events or collisions that we collected. So if we combine these two measurements, these two data sets together, what we can see is a plot to the lower left here. All we need to know is this red line constitutes a level of discovery. So if we, with our black line that we draw, go below this red line, this tells us that we've discovered something beyond what we would have predicted with our non-Higgs boson theory. So clearly at this point here, around 125, 126 GeV, which is approximately the mass of the proton, so about 130 times the mass of the proton, we found a new particle that has some discovery, which led to much fanfare here at CERN and here in Melbourne, where we were hosting the International Conference of High Energy Physics a little while ago. And further to that, it took just 1 year for Francois Englert and Peter Higgs to be awarded the Nobel Prize for the prediction of the existence of this particle that's fundamental to nature. So to go on from this discovery, the physicists at Atlas and CMS often get taken to task about the size of the author lists that we have. So we thought we'd be quite stupid and join together and make a paper with all of us with 5,100 or so authors on there. Luckily, we do this by alphabetical ordering, so Atlas comes first. Adelaide is the lead institution in Atlas, and Jackson is the first on the Adelaide author list. So yes, that's the first author paper for me. And what happened here is taking an average, essentially, of all of these Higgs boson masses that were measured by CMS and by Atlas, and coming up with a lot of complicated studies of the uncertainties and errors that go into this, a very accurate measurement of the Higgs boson mass. It's around here now, which is to 2 decimal places. It's with a small statistical and systematic uncertainty. We're essentially able to show that Higgs boson is no longer a discovery. This was true 3.5 years ago when we were presenting these talks. Now, after 3.5 years of work, the Higgs boson is really a precision measurement. We have a very accurate measure of its mass. The discovery epoch has passed already. And 3.5 years down the line, we have a precision tool to be able to use for our next run of the Large Hadron Collider. And that's really an important thing for us, similar to, as I was alluding to with this Z boson, as we wanted to go higher in mass and understanding it. We can really use the Higgs now as a way to leap forward into a new regime. And so the LHC Run 2, which is the second operation of the Large Hadron Collider, after a couple of years of shutdown and consolidation, we've turned on again in 2015. And I coined this era beyond the Higgs, not only because this is the catchphrase that we're using for our new proposal bid for another center of excellence from the ARC, but also that this is really taking the Higgs boson as this precision probe and using it for us to try and understand other aspects of nature. So earlier in 2015, on April the 5th, in fact, we got first beam into the machine. We'd had 2 years of shutdown where we'd consolidated the magnets going around the ring of the LHC. There's about 1,700 superconducting magnets, so we have to heat them up to be able to interact with them. And we'd made some changes there such that we could go to higher energies. We'd also made some changes to the experiments so that we had better efficiency at measuring a lot of these particles that we produce. And this is showing on the day of first beam or first light, the LHC control center, first thing in the morning, the now outgoing CERN Director General, Rolf Hoyer, along with the Director of Accelerators, Freddie Bowdry. And in the Atlas control room, one of our own here is looking after things. The Atlas shift leader was one of Adelaide's postdocs for this first week of taking data, so we know that that data is right if the rest of it isn't. So what we did for these first few days or weeks of collision would take a lot of these pictures, as I've shown earlier, to really try and understand things and maybe get a little bit of propaganda, I suppose. But from Atlas here in the upper left and CMS, we got some very beautiful first images. And ALICE and LHCb, two slightly more boutique experiments that are being performed using and taking advantage of the LHC collisions, also got some really lovely images from their first collisions. But it's Atlas that we really care about, and here in 2015 we've been working very, very hard to be able to try and take a lot of data. This plot, I'm hopefully not showing you too many plots, but this is showing essentially the amount of data that we've recorded in some units. It's called an inverse femtobond. But this is about the amount of data that we were hoping to record with this experiment over the course of 2015. This is a picture of a mural just outside the Atlas control room where we run shifts 24 hours a day, 7 days a week, and these shifts are done by physicists like myself such that we can ensure the detector is operating successfully. And we've now got lots of data to analyze and results coming in. And essentially the key thing of going from the first run of the LHC to the second run is almost doubling the collision energy. We've gone from 8 TeV collisions to 13 TeV collisions. Now, why would we do that? It comes back to one of the things I talked about quite early on. If we increase the energy, we can probe at smaller scales. And if we increase the energy, we can probe at larger masses. So we could create things with larger masses such that we can measure them and catalog them, and we could also probe at smaller scales to maybe try and resolve additional other features that we haven't seen yet in our standard model. Furthermore, we need to be able to test this picture at a higher energy and see if this holds true as we go up to some higher energy of collisions and see that all of these particles that we showed our precision measurements of are still working with the same accuracy that we saw earlier. And maybe more importantly for this probing of higher masses, we really want to know if that's really the whole picture. So is our standard model of particle physics, these particles that we've been cataloging and measuring, discovering for 100 years or so, is that really the final piece of the puzzle? Or is this really just embedded in some larger or smaller, I suppose, world of additional other particles that we just haven't had the technology to be able to resolve yet in nature or even produce? So this is really what we're trying to be able to get a handle on looking for. Now, in order to do this, I'm going to come back to something I mentioned a little earlier on. When we collide our protons together, we generically call anything that might be outside of our picture here new physics, because it's new to us because we haven't seen it before. So it's not really new, since it should be in the universe if it exists, but it would be new to us because we don't know it exists yet. So the production of new physics could happen with colliding two protons together to make two S particles. I call them S because I have a bias, because I work on something called supersymmetry, and these S's could be squarks that might be an extension to the quarks that we have in nature. If we were to produce pairs of these S's, each of them would decay, and they'd decay, very likely, to some visible stuff, some of the standard model things that we measure, and we can detect these with our experiment, just as we do normally, and presumably also some invisible things. And it's these invisible things that I mentioned earlier that we can infer by measuring all of the visible objects that pass into our experiment, and then looking for any missing energy that might pass out of the experiment and needs to be there to balance the visible things we have. And so this invisible stuff has a term called missing energy. So how do we look for things that are invisible? We could use pictures like this and suggest that we can infer the presence of invisible particles in LHC collisions by essentially looking for missing energy or looking for a signature of what might have caused that missing energy. So imagine someone breaks through a window in your house and they traipse through the house and then disappear because you didn't see them, but they left some little track that they were there, you might be able to infer something about them using your super sleuthing skills of what's actually happened here. So we could infer the presence of a rather standard mass object having passed through our window, or we could infer the presence of something that looks similar but is more massive and is exotic, is new, something that we haven't seen before. And we need to find some ways to be able to come up with being able to reconcile these objects from these maybe newer and more exotic objects. So really, we want to be able to somehow contextualize something we can see in this missing signature, maybe some footprints that allow us to get an idea of what this missing energy really was manifested like. And a lot of us are working quite hard on this type of problem at the moment. The reason for doing this is this may lead us to uncovering something called dark matter and the discovery of dark matter. So I'd like to take a few moments to talk about why that might be interesting or important to do. Essentially because there's evidence for dark matter. There's evidence that there are additional invisible particles that we haven't yet seen in the collider detectors that we have. Indeed, dark matter dominates the mass pi, or the mass percentage of the universe. If we go out and measure the overall mass, essentially it's about a quarter of the mass of the overall universe. The visible things that we're made of, our stars, planets, and galaxies, make up only a tiny sliver of the overall mass of the universe. And there's this large amount of additional stuff. So how do we know it's there? Well, we know it's there even though it doesn't interact electromagnetically, meaning it doesn't emit or absorb or reflect any electromagnetic probe that we could send out to try and look for it, which is the way that we measure everything, if we really think about it. We use electromagnetism to be able to interact with things. But we only see this through gravitational observations. So if we take a look, for instance, at a galaxy and look at the stars in that galaxy, most of the matter is clumped towards the center of a spiral galaxy like this, with things spinning around that center. And the largest gravitational effects are at the center. So we would expect a star that's closer to the center to be spinning much faster, intuitively. And as they get further and further out, there's less stuff. And so there's less and less gravity acting on them. So we would expect, and we calculate something like this red curve, that the effect, the orbital speed would slow down. And what we measure, looking at stars like our own, is something quite different. So what this really means is that out here in the furthest reaches of the galaxy, there has to be something gravitational that's affecting these stars. In order to measure the amount of this, we can look not only at different galaxies, but clusters of galaxies. The universe doesn't just have galaxies strewn all over the place. They tend to clump together and form structure in clusters. And we can measure the mass of these clusters as well. And if we try and reconcile the mass of the visible stuff we see in the clusters with these same orbital rotation curves, these same type of measures of the gravity, it disagrees. There's a lot more matter in there than we can actually see and measure. Similarly, we can look for evidence in a different way. Einstein's going to crop up again here. Einstein's relativity predicted that light would be bent by massive objects. And so if we have a cluster a long way away from us, the Coma cluster in this particular example, light will be bent by a massive object that might be between us, an observer, and that cluster that we're trying to observe, and would be bent toward us so that when we look out to the sky, we might project that this is coming back from some distance directly ahead of us as opposed to being bent away. That light doesn't necessarily just have to bend over the top. It can go down the bottom, and we could see an image down here. And we live in a three-dimensional universe, so the light can bend around all different sides of this massive object. And we would see a cone of light coming towards us, which on our telescope or our eye would be manifested as a ring. This was a prediction of Einstein's. They're called Einstein rings, rather excitingly. And this is essentially what gravitational lensing is. If we were to look in the sky using the Hubble Space Telescope, we can see these various different images of clusters that we see. So there's further evidence of large chunks of dark matter out there in our universe. And we'd like to find out what that is. So this comes back to our particle collider a little bit. And if we just focus on the picture in the middle, there's going to be three possible modes of attack that we could have to try and find out what dark matter is. We've talked quite a bit about CERN and the Large Hadron Collider. So SM here is for standard model. So these are the standard model particles that I've introduced, the protons, for instance. We collide them together. If we happen to increase the energy of our collisions, we might be able to make more heavy particles than we've had the opportunity to make before. So we may be able to directly make and probe dark matter. If we were to look instead at what we call direct detection, where the dark matter would scatter off some normal matter that we would have, we need to take an experiment to a place that has a very, very, very low background. In this instance, that would be in the Stall gold mine, where we're going to be starting the Stall underground physics laboratory to house a dark matter direct detection experiment that will be called SABRE. This will be the first of its kind in the Southern Hemisphere. And this could give us, in a very clean environment, a way to measure dark matter directly impacting on the standard model. Or similarly, aside from direct detection, we could imagine inverting this picture of standard model particles colliding and instead have dark matter particles annihilating into one another, for instance, at the center of our galaxy, where there's a lot of gravitational pull. We assume there should be a lot of dark matter. If we point a piece of apparatus towards the center of the galaxy, we may be able to resolve something quite interesting in that place. And one of the proposed ways to do this is the Cherenkov telescope array that should be coming online in the next 5 years or so. And particularly exciting for us here in particle physics and particle astrophysics is that Adelaide's involved in all of these different wings of attack to try and get some handle on dark matter. And hopefully we'll have something interesting to say about that in the next few years. So the search for a deeper understanding of our universe really requires new technologies to come out on a regular basis, but also requires collider-based experiments to be able to probe more deeply into the fundamental understandings of the building blocks of nature. So on to my next tweetable. I can see you're all enjoying these. So the next line that we've just been talking about for the last 10 minutes or so is that dark matter exists, hopefully I've convinced you of that, and can be produced and measured in particle collider experiments. I saw someone taking a picture, that's great. Okay, so this is the next of the single line summary. I could have just given 4 slides on this, it would have been done. To segue ever so slightly from talking about dark matter, I'd like to talk a little bit about fundamental research and its position in being a driver of innovation. This has always been the case from discoveries that have been made through fundamental inquiry, whether it be physics or chemistry, any of the physical sciences. Again, Einstein's creeping in here, and general relativity is a crucial aspect for something that many of you may have used to be able to get here accurately today, and that's the GPS that you use in your phone, or maybe you have a GPS unit in your car. If this wasn't corrected using general relativity, you'd be way off after you started to drive a long distance. And this is quite crucial. James Clerk Maxwell's work into electromagnetism was also critical, even though he didn't have a cell phone himself, for all of the mobile communication devices that we make and have really revolutionized our world in the last 20 or 30 years. This research had nothing to do with the things that we actually use from it, but it certainly was critical to be able to get there. And who knows if we would have reached this position in our understanding as quickly if it wasn't for this physics research. But our current physics research is no different, and so I'd just like to almost finish up with touching on a couple of things that the Adelaide group's doing at CERN. I talked a little bit about searching for supersymmetry. We're really pioneering some new ideas to search for supersymmetry, and in particular, coming up with some new techniques and ideas to be able to interrogate the data sets that we take at the Large Hadron Collider. And this is some new set of kinematic variable approaches to analyze the big data sets that we get in the LHC. We've been doing this closely with our friends and colleagues at Harvard University, and we had a first workshop there a couple of months ago, which was very exciting, hopefully the first of many. We also in our group hold several leadership positions in the Atlas collaboration and have a long history of having worked on the building of the current and operating the current silicon detectors of the Atlas experiment, the innermost detectors, the first things that the remnants of the proton-proton collisions see. Several of our group were involved in building these, and we're now actively involved in upgrading them for further upgrades toward run 3, 4, and beyond of the Large Hadron Collider. But it's not just this work at CERN that we do. We're quite aware of the optics of our research, and we do work beyond just particle collisions, beyond just the kaleidoscope. I've already mentioned, but it's probably worth reiterating, the state and federal funded Stall Underground Physics Laboratory, where we're pressing ahead with having the first ever direct dark matter detection experiment of its kind in Australia and in the Southern Hemisphere. This will be a very exciting time. We work with researchers a little closer to home at the other end of North Terrace, and this week we've submitted a paper on the simulation of cyclotron radioisotope production on a solid target, which is very exciting. We also work on testing optical fibers that can be used for measuring beam losses. If we're going to build future accelerators, we need to ensure that we're not being wasteful with the beams. It's very expensive to put these things into your storage ring in your accelerator. And we found that optical fibers are a great way of traversing a long length of maybe a linear accelerator or some larger facility that we might have to understand the stability of the beams we have. One of our Adelaide physicists is the co-leader of a new data mining tool that's going to really be a sea change in the way in which we combine all of the different data sets from all these different types of inquiry that I talked about, whether it be indirect and direct detection of dark matter or various different other collider particle experiments. And so this is really going to be very exciting, and I fully imagine will be able to be used and manifested in a wide variety of data mining tools. And not least, we're developing some high-speed electronics to be able to read out and measure these particle collisions that happen at a really alarming rate in our colliders, such that we're able to get accurate readouts of the particles that we create. So I think that's about it. One last tweetable, since we're so excited about these. The University of Adelaide physicists are leaders in collaborative and innovative research. And that's not just particle physicists, that's everyone in the Department of Physics. We're really doing an awful lot of things outside of the scope of just our own individual research. And there's a lot of work going on here. So any of you that might be interested, or any of you that would like to find out more, or certainly come and be a student with us, we'd be very happy to talk to you about this. So that leads me to the conclusion, which I changed to be conclusion for now. This is a very dynamic field, high energy physics, and it's changing over the course of months and years. So we can't really conclude on something. We're still moving towards goals that will be pushing towards the next 10 to 50 years as we try and probe deeper and deeper in our understanding. That being said, there's very good reason to expect there could be discoveries at the Large Hadron Collider, but beyond what we've already discovered. And these, as we're opening up this new era of data exploration, could happen any day now. Pioneering research in particle physics creates unique advances in knowledge, from new applications to cutting-edge technologies, and ultimately transformational opportunities. So this is hopefully something that you've got a taste of. And the one thing I generally do like to finish with is a mention of students. They really are the lifeblood of all of these experiments. The students are the people going out making these measurements and doing this work and running the detectors. And so at this point in time, with turning on at a new high energy, this is really an incredibly exciting time for PhD students in particle physics, be they starting this year or in the coming years. We're all very fortunate to be in this position, and it's truly a unique opportunity, so it's one we should enjoy. So I'd like to thank you very much for your attention.
I'd like to just mention something about dark energy. That big slice, very tantalizing on the picture.
Yeah, I think dark energy is something that we should have another expert come and talk about at some point in the future. But this is more related to the fact that space itself is expanding. So not just the gravitation of the dark matter that we see looking into galaxies, but actually space itself is expanding. And so there's energy that's being born out of this from the expansion of space itself at the fundamental level. And measurements recently went to prove that there was quite a radical difference in what we were expecting to see vis-a-vis the expansion or acceleration of space, and the fact that we've really seen this huge amount of energy that we didn't anticipate would have been there. So really, dark energy is more related to the expansion of space as opposed to gravitational matter, which is what dark matter is related to.
Thank you, Paul, for a most informative and enjoyable talk.
Thanks.
Is there a theoretical upper limit to the amount of energy that you can apply to the Large Hadron Collider? You're working at 14 TeVs at the moment. Can you go higher? How far?
So that's a good question. At the moment, we're working at 13 TeV. We're a little too scared to go to 14 TeV at the moment, but still, it's safer, and we feel we can do a lot of physics at this energy. But the design energy for this experiment was 14 TeV. The reason being, we already had a tunnel built from a previous experiment that we had, the LEP collider that I showed during these experiments early on in the talk. And this sort of sets the scale of how high we can really go in energy with the technology that we have at the time. There are plans to be able to take the Large Hadron Collider and do something similar to what was done with previous colliders and sort of bootstrap this up to an even bigger tunnel, but you need to build a ring for this. So that would require an 80 or 100 kilometer ring, or a new facility potentially in China. The Chinese are very excited about maybe building a new high energy collider. So there is a limit to where we can go with the LHC technology, and with just the constraints of the size of the tunnel that we have. Yeah.
How much pre-programming is there before each test program? Is it like a week, a month lead time, or?
So by test program, you mean colliding of the beams? Yeah, okay. So we tend to have some shutdown periods throughout the year. So for instance, there will be some shutdown over Christmas, and this will last until approximately April or so of 2016. The reason for that over the winter tends to be the cost of electricity more than anything else. It's a trade-off between people in the France area of CERN being able to turn their heating on and physicists running the LHC. Most of those physicists live in that area of the world, so obviously we're not going to be running some experiment, but also the cost of electricity does go up at that time of year, so it doesn't really make financial or just social sense to be able to do this. But even when we're running, there is a schedule throughout the year where there'll be some machine development time for the LHC accelerator physicists to maybe do some tests that they might want to do to be able to shrink the size of the beam or play with different aspects of the proton beams such that we could, in principle, enhance the luminosity, one of the other characteristics of the beam, such that we can essentially shrink them to get a larger probability of protons actually colliding every time we bring them together. So this would increase the amount of data that we get out. So there's, over the course of the year, different periods of time where there are machine developments and proton runs and other things that are happening with the LHC. Yeah.
When you collide the particles together at such high speeds, does it damage the machine at all? Or how can the machine withstand an energy release of the collision of the two particles?
That's a good question. So we have two separate things to this. One, the machine is what we would call the LHC, and then the detectors would be the different things where we measure the particle collisions. So we need to be sure of the integrity of the beam going around the machine, such that it's well controlled within the magnets that we have to send it around the ring. Obviously, this has to be done with a very high accuracy. And there's a fail-safe, which is called a beam dump, where we're able to essentially switch some magnets and dump the beam and then start filling the beam again over time. So if we're not happy with the integrity of the beam, we can do this. For the detectors themselves, then that's a very important question, that we really don't want the beam to go off its axis, if you like, and fire particles into the detector, which could be potentially catastrophic. There are a lot of fail-safes against this. We have beam position monitors and beam loss monitors around the whole ring, but particularly close to the interaction regions where we collide the protons together. So this gives us a way to be able to measure radiation, in a sense. We have this using various advanced silicon detectors, but also diamond sensors. So diamond's one of the strongest substances in nature. We're able to use this as a way to measure beam position without the detector itself suffering a lot of radiation damage. So it's a very important thing, because you don't want to build something that's complicated and then just mess it up because you make a mistake one day. So you really have to understand this aspect of the experiment, yeah.
Why did you build the Large Hadron Collider in Geneva? Why didn't you pick a nice flat plane somewhere? Was it because of the cafes, or?
Was it because of the cafes? Well, I didn't build it, that's one thing, so I didn't get a say. But, I mean, I think a lot of this has to do with the diplomacy of CERN being formed as a body, in a sense. Geneva, historically, is an area where Europe has come together in peace and done things in a collaborative place. It's maybe not the best place to be able to do the civil engineering for something like this, but it's a place where all of the various different member states of CERN have now quite a long history in doing their collaborative science, and I think it's hard to replicate that type of institution in a different place with all of the various scientific and political agreements in place. So it really is coming from a place where there's trust from the governments and the people. The scientists at this lab have done this type of work before. They really know what they're doing, and it's very likely they'll get the job done right if they do it in this lab infrastructure, as opposed to going to some other site that maybe would be easier to do the engineering in. It's just not necessarily going to be the best place politically to do the work.
One more question.
All this is built on the collision approach. Is there any other fundamentally different method of research that's being considered in the background that could make the Large Hadron Collider obsolete?
I hope not, but it's a very good question. So I think obsolete might be perhaps too strong a word, but something that would have synergy with the particle colliders, because, of course, as I think maybe you're thinking, to go to higher and higher energies, we have to keep building bigger and bigger machines, and maybe this just doesn't scale forever. We can't keep doing this. So we do have to come up with better ways, perhaps, of getting these energies with smaller accelerators. Similarly, we're seeing the highest energy particles that we ever measure impacting on the top of our atmosphere and showering particles onto the planet that we can measure as well. And so to measure very high energy probes from quite distant objects in the universe, we can really use experiments like this, and there are people here at the University of Adelaide working on the Pierre Auger Observatory in South America that does exactly this. So I don't think it renders the collider obsolete, but it's sort of a synergistic approach to trying to look at this fundamental science, and there could come a time when really we just can't keep probing at higher and higher energies unless we really improve the technologies that we have to cut down the costs of engineering something like this.
What's the highest speed that the particles are going at?
The highest speed the particles are going at is 2.9999999 times 10 to the 8 meters per second. So it's a fraction away from the speed of light. I think it should have been 6 nines, but I lost count. And it's essentially, you can't accelerate something to the speed of light that isn't already there. This is a caveat of special relativity. So we're getting these protons to as close to the speed of light as we can within the LHC, and also the different booster accelerators that we use to be able to feed and inject the protons into the LHC. So we're getting them essentially close to the speed of light before we collide them together.
Okay, I've got one or two more questions to finish up for you, Paul, but I remember just over 3 years ago when the big Higgs boson paper came out, And I've got the title here. I'm going to read it because it's so beautifully simply expressed. But it's Observation of a New Particle in the Search for the Standard Model Higgs Boson with the Atlas Detector in the LHC. Have you read that? Published
twice,
in
yeah.
Physics Letters B in September 2012. And I remember thinking at the time, Peter Higgs, and no doubt his other colleague that were to win the Nobel Prize, decades ago, they would have had, it was really a Star Trek fantasy, wasn't it? I mean, it couldn't possibly roll, could it? It was crazy. And they must have felt pretty good when the results came through. Somebody also felt pretty good was me, because I had a look at the paper, and there are 178 institutions listed as affiliations of the many authors. Do you know how many authors there are?
About 3,000.
A lot.
Yeah.
178 institutions, and as I think Paul alluded to earlier, the University of Adelaide is listed as the first institution, and I thought to myself, that's clearly because we're the most important contributor. Of course, it turns out that we are, but we're also first in the alphabet, unfortunately. Now, Paul, can you tell me how many Jacksons there were in the author list?
The whole author list, there are, I think, 3.
Correct. Correct. And one of them is this guy. And I must say, I would feel incredibly proud if I was a co-author in what is a phenomenally important paper. So congratulations to you, Paul.
Thank you.
Congratulations to your team. We are indeed extremely proud of physics here at the University of Adelaide, and it's a great credit to you guys that you've done such amazing work, have phenomenal networks around the world, and please join me in thanking Paul for a wonderful talk.
Thank you very much.